Welcome to Pomodoro Joe for Friday, July 28th, 2023. Today we're doing LeetCode problem 486, predict the winner. This is a medium problem. You are given an integer array nums. Two players are playing a game with this array. Player 1 and Player 2. Player 1 and Player 2 take turns, with Player 1 starting first. Both players start the game with a score of 0. At each turn, the player takes one of the numbers from either end of the array, i.e. nums 0 or nums at nums length -1, which reduces the size of the array by 1. The player adds the chosen number to their score. The game ends when there are no more elements in the array. Return true if player 1 can win the game. If the score of both players are equal, then player 1 is still the winner. You should also return true. You may assume that both players are playing optimally. Alright, and then we have some examples. We have 1, 5, 2. Player 1 goes first, so they have to choose either 1 or 2. So it doesn't matter which one they choose. Player 2 will then choose 5, and player 2 wins the game because 2 plus 1 or 1 plus 2, either way, player 1 has fewer points than 5. So we'd return false. Alright, so we'll not do C++, let's switch this over to Python. Let's put 25 minutes on the Pomodoro timer and we will get started. So, fortunately, I've seen a problem like this before, so I know there are a few tricks that we can use to make this a little bit easier on ourselves. So for this one, I'll be using a recursive function to go through, basically choose either option or both options. We can choose from the left side or we can choose from the right side. Either way, we'll try both options, see which one gives us the best score. Along the way, we'll have to pass down the new bounds of our array. We'll also have to pass down whose turn it is, and we'll have to pass down some scores. All right, so we'll start with our recursive function. Predict the winner recurse. Okay, so we'll pass in the left and the right index. We'll also pass in which player this is. Now here we can either pass in both the players' scores, so player 1's score, player 2's score, or we can use a trick. We can use a relative score. So for this one, we'll use that trick. So anytime you have a problem where you have two players and you need to just determine which one is the winner, you can use a relative score. So instead of keeping track of the actual scores of both player 1 and player 2, we'll be keeping track of the relative score between player 1 and player 2. They both start at score 0, so our relative score is 0. No one has an advantage. When we get points for player 1, we'll add that to our relative score. So as player 1 gets more points, that score, the relative score, will go up. When player 2 gets points, we'll subtract those points from our relative score. So our relative difference between the two players will go down. At the end, if our score is 0, both players had the same number of points, we can say player 1 is a winner. If the relative score is positive, then player 1 had more points than player 2. We don't necessarily know how many points both players have, but we just know player 1 has more points than player 2, so we can return true, player 1's the winner. But if our relative score is less than 0, that means player 2 had more points than player 1, and we return false. So we'll have a relative score here. All right, now let's do our base cases. Since this is a recursive function, we'll need some base cases. So for our first base case, let's just check our indices and make sure that we're not out of bounds or we haven't exhausted our entire array. All right, so if our left index is greater than our right index, then we can just return the relative score. Now the next one, if they're the same index, that means this is the last turn. So if the left index is the same as the right index, that means whoever's turn this is, they get that last point or the last element in our array. So for this, we can check to see which player this is. So let's actually define our players out here. Player 1 will equal 1. And player 2, I can make this all capital actually, let's do that. So for now, we'll make player 2 equal to 2. Just to make it easy. Now, that might change. All right, so if this player is player 1, well, then we can take these last points, add it to our relative score, and return the relative score. If it's player 2, we subtract these last points from our relative score and return it. Okay, so this is our other base case. If we're on the last element, the left index and the right index are the same, we'll just check which player this is. If this is player 1, then we'll add this last element to the relative score and return it. If it's player 2, we'll subtract the last element from the relative score and return it. All right, so now if this is not the end of the game, then we have two options. Whichever player this is, they can take the element on the left side or they can take the element on the right side. So we have two options. Let's start with player 1 and then we'll do player 2. So this player 1. All right, so we have two options. Option 1, we take the left-hand side, and option 2, we'll take the right-hand side. So let's put that here. All right, let's take this new relative score. So that's going to be the relative score plus the element at the left index. All right, so we'll have our new relative score, and then we'll call this recursive function. So option 1, we take the left element, so our left index is increased by 1. The right index doesn't change. The player switches, so this was player 1, so now we have player 2. And the relative score has changed, so we have a new relative score. All right, so that's option 1. Now option 2, we'll take the right-hand element. All right, I'm just going to copy this because it's basically the same, just with the right element. So the new relative score for the right side will be the relative score plus the new element on the right index. This is option 2. Let's see, and our left index stays the same, but now our right index is reduced by 1. We have to move it closer to the left index. Still switch to player 2, and we still have our new relative score. All right, so this is if we were player 1. We have two options. We take the left element or we take the right element, and that score gets added to the relative score. Then we recurse on the remaining elements. Okay. What about player 2? Now we haven't talked about the return value here. Let's talk about the return value. So what's the return value for player 1? Option 1 or option 2? Well, we're trying to maximize our score. Player 1 is trying to get the greatest score. So we'll return the maximum of option 1 or option 2. All right. Otherwise, this is player 2. So this takes care of player 1. What if we had player 2? We'll basically do the same thing, but instead of having the new relative score be the sum of the relative score and this element, we'll be subtracting that element's points from the relative score. Remember, player 1's points get added and player 2's points get subtracted. So we'll just swap these around to subtraction. We'll also have to swap this around, so this is player 1 now. But everything else is the same. Now, what do we return for player 2's return value? So this is where it gets a little bit tricky. So player 1 is trying to maximize the score because player 1 wins if the score is positive or 0. But player 2 is still trying to play optimally for player 2, but player 2 only wins if the score is negative. So player 2 is really trying to minimize the score. So for player 2, this was player 2's turn. Actually, I should write this here. So on player 2's turn, player 2 wants to minimize the score. So in this case, we'll return the minimum of these two options. All right, So this should handle all of our recursive cases. And finally, out here, we'll still need to call this recursive function for the first time. So our result here, that will equal our recursive function. Let's see. The left index is 0. The right index is the length of nums minus 1. That's the max index. Our player, we're going to start with player 1. And our relative score starts as 0. Now in the end, we do need to return a true or false. So in this case, we return whether or not our relative score, or our result here, was greater than or equal to 0. So anything greater than or equal to 0 means player 1 wins, otherwise player 2 wins, so we return false. All right, so this should do it. Let's see how many typos I made. Okay, so this works. Let's see if we can pass all of the tests. And we pass. We don't do great, but we do pass. We beat about 15% for runtime and 99% for memory. Wow, we do great on memory. All right, let's jump back here really quick. So a couple things we could do. This is the very basic, straightforward way of doing this. We can do some memoization or some caching. So let's do a quick and simple test here. Let's just add cache, see if this gets us anything. So with caching, this will take the inputs. When we see the same inputs again, it will just return the cached value of the output. So this might save us a little bit. Let's try it. A little bit. Now we're up to 26%, but it kills our memory. Now we're down 7%. Wow, that's terrible. All right, let's get rid of that cache. So one other thing we could do here. This is a lot of code. This is a little bit confusing if you tried to just quickly scan through. One thing that's going on is we have this player 1 and player 2. Player 1 is 1, player 2 is 2. What if we made player 2 -1? It doesn't have to be 2. We could say player 2 is -1. That means here, instead of just passing player 2 in, we could pass in negative of whatever the player was. So player is 1, player 2 is -1. So that means we could take this and swap this around and make this negative player. Same thing here. This is negative player. So this just switches which player we're on. We can do the same here and here. So now these are looking actually almost exactly the same. Left index +1, right negative player, relative score, left index +1, right. Yeah, these are exactly the same now. So the only difference between these two conditionals is here we're adding our nums and here we're subtracting our nums. Well, what if we just use a multiplier? Now our player can be a multiplier. So if we multiplied our nums by player 1, it just is nums, and we're fine. If we multiply it by player 2, this will turn to a negative nums left index, which is exactly what we want to add. So we could actually condense this. We don't need to do this check if player 1, else player 2. We can do the same thing, but just using a multiplier on these values here. So let's do that. So let's grab this whole thing. We'll bring it out here. All right, we need to do some adjustment on the tabbing. All right, so now we're going to multiply this by the player. And same thing here. So again, if this is player 1, this doesn't change anything. This stays positive. If this is player 2, this will become a negative value and we'll be basically subtracting from relative score. So that takes care of this. Now, what about the return values though? So the return values, in this case, we want to return the maximum. Player 1, we return maximum. For player 2, we return the minimum. So we're still going to have to check to see which player we have for our return values. All right, let's just do that down here. So for this, we'll have maximum if it's player 1. And minimum if it's player 2. All right, so we'll return the maximum if it's player 1, otherwise we return the minimum. And actually we don't need this result, we can just do the return. And that means we don't need any of this anymore. Wow, that really makes things way more compact. So this does the same thing that we did before, but instead of checking explicitly for player 1 and player 2, we're using basically players as our multipliers. So we'll go through, do the same thing we did before, just return the max if it's player 1, otherwise the min. All right, let's just see if this works. So this still works. Let's submit that. All right, it still works, but I don't think we do very well. We're at 13% for runtime, 43% for memory. So that actually takes more memory. That's interesting. Would not have thought that. We actually don't need these anymore because we're not using them anywhere. So let's get rid of those. I guess we're using it here, but we could just do essentially the same thing we did down here. Relative score plus equals nums at this index times our player. We don't need this conditional anymore, so we could just do this. All right, that cleans things up nicely too. Okay. Make sure this still works. And it looks like I'm still using player 1 somewhere. Right, we'll just pass in 1. Okay, so that still works. I'm a little bit curious. I don't think we need this because we're only going down 1 at a time. So we should get to our equals case before we ever get to that other base case. Let's just run that. Okay, so this might save us something. We're reducing this by 1 conditional check and a couple of variables. Doesn't really save us that much. We're still better in memory now, back to 97%, but we're only at 16% for runtime. Yeah, not great. But this is looking way more compact. This is a lot easier to read through and reason. All right, one last thing we'll do before we call it. We'll put this caching back, and then we'll also try our own DP. So I guess this is 2 things we'll do. So this should give us a little bit of a bump in runtime, and it's going to take a hit in our memory. So yeah, we're up to 26% for runtime, but we're down to 7% in memory. So that's a huge trade-off. Okay, last thing we can do here. We can do our own DP. So this is just memoization. It's going to do the exact same thing that the caching was doing. We're just going to be doing it manually instead. So we'll have DP, and this will be some dictionary. So the key will be basically all of these inputs as a tuple, and the value will be whatever we return. So first thing we'll do is check. If, well, let's create our key first. Let's do that. So we create our key, and our key is literally just the tuple of these arguments. So I'll just grab this. That's our key. And if the key is in our DP, then we can just return DP for this key. So we've stored the value in there. We'll just return that value. We don't need to run this again. Next, anytime we see a return, so we've got 1 here and 1 down here, we'll actually have to replace, or not replace, but before the return, we'll have to add this value to our key value store. So let's go down here, DP for this key. That's going to equal this relative score. Same thing down here. DP for our key will equal this. And then we return DP for our key. So this does our own caching essentially. Still works. Let's see if this gets us anything. All right, so we're at about 26% for runtime, 7% for memory, which compared to the cache decorator, it's exactly the same. There is no difference at all. So we did our own DP. Doesn't really make any difference between using DP or cache, so just stick with cache when you're in production code. Okay, we are close to being out of time, so I think that is it for me. There are other ways to do this. There are clearly better ways to do this because we only got a 20-something% for runtime. There must be much better ways to do this, so I recommend checking those out. We can actually take a quick look. Let's do that. Quick look here. Somebody's doing awesome. Check this out. Super short code. All right. So they're using DP as well. Oh, but they're using DP for the entire length of the nums. Interesting. I'm going to have to look at this one a little bit more closely because right off the bat, I'm not seeing exactly how this works. But you should check this out. So yeah, check this one out. Anyway, that is it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.